My name is Christos Lougiakis and I am a PhD student in the Department of Informatics and Telecommunications of the NKUA. In this presentation, I will guide you through the progress I have made in my first year, studying the literature and technologies related to VR interaction and perception, as well as the research plans that me and my supervisor Maria Rusu have for the future. They have been summed up in the title Physics-Based Grasping in VR using different tracking methods and reinforcement learning, the effects on the sense of embodiment. But let's see briefly what that means. Grasping with our virtual hands in VR is one of the main interaction methods of object manipulation. The visual feedback is a very important factor for the sense of the body ownership and the performance of users when grasping virtual objects, so it must be realistic and intuitive. Physics-based grasping covers fully these requirements and may be the best option. There are multiple relevant studies to physics-based interaction, but their outcomes and results are limited by the fact that were conducted using the Leap Motion hand tracking device, exploring only one type of user input. Some types of user input don't offer full control of the fingers, and although in robotics reinforcement learning techniques have been used to teach human-like hands to grasp objects with great results, to our knowledge there are no studies applying this approach to VR interaction. Lastly, although there are several studies exploring the user sense of embodiment while they interact with their hands in VR, none of them have been conducted incorporating physics simulation. Based on these observations, we aim to study the following research questions. 1. How well can a runtime physics-based grasping method perform for user interaction in VR using different input tracking techniques that offer various levels of finger control, and what are the differences? Second, can a reinforcement learning approach be applied to the setting of RQ1 in order to produce realistic and generalizable grasping strategies for tracking solutions that offer limited control of the fingers? And third, how do the physics-driven user interaction and object grasping of the previous questions affect the user's sense of embodiment? To answer these questions, we propose the design and development of an improved physics simulation extension to the existing library Hand Physics Toolkit that offers a platform and device agnostic solution for physics interaction. The extended library will then provide a framework for testing different input devices for hand tracking under the same environment and will serve as the training ground for the reinforcement learning agent. In return, this will give us the opportunity to run user studies measuring the performance, preference, and sense of embodiment of the users in these different contexts.